Okay, so welcome back. Today's lesson is going to be about two very important theorems. So this is now notes for 13.5. We're going to talk about the conjugate root theorem, which once you see what it is will be very easy to remember based on the title of the theorem. And also we're going to talk about Descartes' rule of signs. Okay, so let's just get started. Conjugate root theorem. If a polynomial f of x has real coefficients and a plus bi is a root, you guessed it, then a minus bi, its conjugate, is also a root. So if we have polynomial with real numbered coefficients, if we know that 3 plus I is a root, then 3 minus I is a root, and vice versa. Okay? Adding to that, if the polynomial has rational coefficients, and a plus b root c is a root, then its conjugate, a minus b root c, is also a root. So the conjugate root theorem can be very useful in solving equations that are bigger than quadratics. If you know one of the roots already, automatically its conjugate will also be a root. Okay? So we'll do a quick example. Solve the equation two x to the 4 minus 13x cubed plus 18x squared plus 23x minus 60 equal to 0, given that 2 plus I is a root. And I didn't write this out, but conjugate root theorem is right here. Okay, sorry about that. Okay, so because of the conjugate root theorem, so here I have this complex root, and all my coefficients are real numbers. So that means that not only is 2 plus I a root, then we know 2 minus I is also a root. Okay? Which then means that this equation, 2x to the 4 minus 13x cubed plus blah, 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 and so on and so forth. If these two are roots, then I know that the two factors are going to be x minus 2 plus I, and then x minus 2 minus I, times, let's see if we can figure this out. We have a quartic. This is just linear. This is just linear. So in here, we're going to have some quadratic. And you guessed it, if we divide these two, whatever these two give us when we multiply it out, if we divide that into the original equation, that'll give us that quadratic. And we know how to solve quadratics, either quadratic formula or maybe it factors nicely. Okay, so you have two options here. You can either multiply this out, do it the long way, or again, I like to use a shortcut. If we treat 2 plus I and 2 minus I as the two roots, when you add them, you get 4. When you multiply them, you get 4 minus I squared, which is the same as 5. And since we know that R1 plus R2 is negative B, and R1 times R2 is C, I'm just going to go ahead and combine these two together to make x squared minus 4x plus 5. Okay, and now that I know that this quadratic divides perfectly into this quartic, I can go ahead and divide it with long division to figure out what that is. So x squared times 2x squared gives me 2x to the 4. So multiply 2x squared to the divisor, you get 2x to the 4 minus 8x cubed plus 10x squared. And now we subtract column by column. This cancels. Negative 13 plus 8 is negative 5x cubed. 18 minus 10 is 8x squared. And we bring down the next term, which is 23x. Repeat the process. So now I'm looking at x squared and negative 5x cubed. I know that if I multiply by negative 5x, that will do the trick. So multiply negative 5x to the polynomial on the outside, you get minus 5x cubed plus 20x squared minus 25x. Subtract each column. These cancel. 8 minus 20 is negative 12x squared. 23 plus 25 is 48x. And then bring down the minus 60. So now, same game. X squared times negative 12 will give me negative 12x squared. And again, take negative 12 to every term, so that's plus 48x minus 60. Notice these are identical, so when you subtract, you get 0. That should happen. We knew it was going to happen because this was a factor of the original equation, which means that when you divide by one of the factors, you should get something that's quadratic with no remainder, which is exactly what happened. Okay, so now to find the other roots, you can use the equation 2x squared minus 5x minus 12, set that equal to 0. It looks like we can factor this, so we don't even have to use a quadratic formula. 2x plus 3 times x minus 4 looks like it gives me negative 12 and 8. Negative 8x plus 3x gives me negative 5x, so we're good. The other two roots are going to be negative 3 halves and 4. So if we were given that 2 plus I is a root, 2 minus I is one of the other ones in addition to the one they already told us. So these are the 4 solutions for that equation. Okay? So this technique also works whether they're complex or just irrational conjugates like a plus b root c. Same scenario, if these coefficients are rational numbers like they are here, you could have also been given something like 1 plus root 5. So then you would assume 1 minus root 5 is also a root, and then you do the same exact steps that we did here to find what quadratic that creates, and then you can take that, divide it into the original equation to figure out what's left over, and then solve whatever is left over to find the remaining roots like we did here. Okay? All right, last thing we're going to do is talk about Descartes' I guess it would actually be, oh, I'm not an English teacher. Someone can correct me. His name is Descartes with an S at the end, so I would assume it's apostrophe S. It always tricks me up. My excuse is I'm a foreigner. So maybe I'll go back and change this. Okay? All right, so Descartes' rule of signs. This is more of a theorem that'll help you narrow your search and focus your search on finding all the roots of a polynomial or an equation. Because if you know going in that there's no negative roots, you can eliminate half of the educated guesswork just by knowing that. Okay, and Descartes' rule of signs might be able to help you with that. Okay, so here's how it works. So let's say, well, there's two possibilities. Let's call it 1. The number of positive roots in a polynomial is either equal to the number of changes in sign of f of x, or is less than that by an even amount. The second part relates to the amount of negative roots, so the number of negative roots, and it's the same verbatim. The only difference is we're going to inspect f of negative x instead of f of x. Okay, and I think this will make more sense when we do an example, but all you do is look at the original polynomial, which is f of x, and you look at the coefficients. If they're all positive, we say that there's no change in sign. They don't change from positive to negative, so there's no changes, so we say that there's 0 sign changes, which means that there's 0 roots. If f of x, and I'm still talking about positive roots, if f of x has, let's see, 4 sign changes, so maybe it goes from positive to negative, and then from negative to positive, and it alternates back and forth like that, and there's 4 of them, then the theorem or the rule of signs guarantees that there's either 4 positive roots, or it's less than that by an even amount. So if you just keep subtracting 2, that gives you all the other scenarios. So there's either 4, 2, or 0 positive roots. And it works the same with the negative roots, but we have to inspect f of negative x in order to do that. Okay, so here's what it looks like. Maybe we'll do a couple of examples because these don't take very long, but it's good to have a few of these. Okay, so let's say we have x cubed plus 8x plus 5. Let's say that's f of x. And we just want to discuss the nature of the roots. Sometimes you might be asked to tell me what you know about the roots, not necessarily to find all the roots, but just tell me what they kind of look like. And Descartes' rule of signs will help you do that. Okay, so first what we do is look at f of x. And you see that out here we have a positive 1, a positive 8, and a positive 5. Which means that there are no sign changes for f of x. F of x has no sign changes, which guarantees that there are no positive roots. Okay? So now what we'll do is look at f of negative x. And now I'm going to go ahead and write this out first. So if I plug in negative x and cube it, I get negative x cubed minus 8x plus 5. So now when I'm looking at f of negative x has, let's see, we go from negative to negative, so that's no change. But then from here to here, we go from negative 8 to positive 5, so that's one sign change. So what that means then is that f of x, the original equation, has one negative root. So in this scenario, we're actually pretty specific about what we know. We know that there's no positive roots at all for this, and we know that there's exactly one negative root, which gives us some information about the other two roots. Because since you know that this is cubic, including multiplicity, you know that there's going to be a total of 3 roots. So if all we have is one negative root that's accounted for, then we know that there's going to be 2 other roots. Okay? Now obviously 0, because we're talking about positive roots and negative roots, 0 doesn't work. You should always check that, but 0 plus 0 plus 5 certainly doesn't give us 0. So 0 is not an option. So if we have no more positive roots, no more negative roots, and all I have is 1 so far, I know that f of x has one negative root, and because of what I said, we know that f of x has 2 complex conjugate roots. Okay, and we're going to be kind of loose with this. Complex is actually going to refer to non-real numbers. Obviously, these are going to have to be imaginary in this scenario, okay? Because if all we have is one negative root, 0 does not work, and there's no positive roots, there's got to be 2 imaginary answers to give us a total of 3, okay? So you can say f of x has 2 imaginary conjugate roots, or 2 complex non-real conjugate roots, or if you just say 2 complex conjugate roots, I'm going to be okay with that, with the assumption that complex refers to a plus or minus bi, okay, with an actual imaginary term. Just kind of easier to say it that way. All right. Sorry, we'll do one more quick example with the rule of signs. Let's say we have f of x equals x to the 4 minus 3x squared plus 4x plus 8 equal to, well, no, that's fine. Okay, so same scenario as before. Discuss the nature of the roots. So we'll start by looking at f of x. We have a positive to a negative, so that's one change. Negative to positive, that's 2 changes. Positive to positive, we're good. So f of x has 2 sign changes. So that means that f of x has either 2 positive roots, and don't forget that Descartes' rule of signs says that it's equal to the number of sign changes, or maybe it's less than this by an even amount. So if you subtract 2, it's possible that there's 0 positive roots. Okay? Let's just run through all the scenarios. If there were 3 sign changes, then you would say there's either 3 or 1 positive root. If there's 4 sign changes, then you would say 4, 2, or none. 5, you would say there's 5, 3, or 1. Okay, does that kind of make sense? And then let's look at f of negative x. So I'll write that out. Plug in a negative and raise it to the 4th. That stays x to the 4. Plug in a negative and square it. Doesn't do anything. But now here, if I multiply by negative x, we get minus 4x plus 8. Okay, so now let's see. F of negative x has from positive to negative. That's one change. Negative to negative, nope. Negative to positive, though, that's another change. So f of negative x has 2 sign changes. So that means that f of x could have 2 negative roots or 0 positive roots. I'm sorry, 0 negative roots. Okay, so here's our discussion. So in conclusion, we have to go through every case. It could have 2 positive roots and 2 negative roots. And there's our total of 4 for a degree 4. It could also have 2 positive roots and then 0 negative roots. And again, 0 is not an option. So if it's not positive, if it's not 0, and it's not negative, then there has to be 2 other imaginary. So we'll say 2 complex conjugate roots. Okay, so that takes away all the possibilities with 2 positive roots. The last one would be if there's 0 positive roots. If there's 0 positive roots, then I could have 2 negative roots. And again, 2 complex conjugates. Or I could have 0 positive and then 0 negative, which means I have all imaginary answers. So what I would say then is that there are 2 complex conjugate pairs for a total of 4. So we have a plus bi, a minus bi, and then another pair, 4 roots total here. Okay, so that's kind of how Descartes' rule of signs works. Tomorrow, again in class, you'll have a chance to ask questions and work on some practice problems. All right, farewell.